think it's this one or this one. Probably either one. Okay, so now, so imagine we can mimic what we just did over there. So try to view this as your eye is on this side, on the right side, and you see you have field lines coming out of the north. Why do they have? Yeah, okay. So you see the red line means the field lines are coming out of the north this way. So if we want to mimic the first situation, we can kind of bring this here and say, okay, the field here, we have a field, show field, field strength. Magnet, show compass, show field meter. Oh, nice. Perfect. So you see the field strength right inside of the coil is 3 Gauss right now. So I can bring it close. Okay, let's say the field strength is around 10 to begin with. 10 Gauss. Okay, now then we can change the number of loops. We could change the loop area. Okay, let's say keep it like that. Okay, so now the field strength is about 8. Oh, okay. Here in this case, it's not uniform, right? Because the field strength of a magnet is strongest here at the central line. Over here, it's probably weaker. Okay, so now let's change this. Let's go from here to here in, let's say, 1 second. And then watch here the direction of the voltage. You see, right there. You see here? So then you go like this from here. You go inside. And then this one deflected all the way to somewhere here, right? Okay, so let me repeat that again. From here to here, I'm going to do it in a second. So what should have been that deflection? Can we do the math of that? What should have been the magnitude of that deflection? If we care about calculating the electric field, we can just focus on the EMF, and that'll be negative N d by dt phi b, right? And then the EMF will be negative, in that case, how many loops do we have? 2 loops, right? Yeah, just 2 loops. And then the area is just going to be pi r squared. And then B final minus B initial over delta t, right? Negative the 2 loops. What's the radius of that? I guess I'm going to assume that the dimensions of the simulation are realistic. So from here to here is going to be around, I'm just going to measure it with a ruler. So let's say the dimensions come out to be 2.5 centimeters. Okay, so the radius of that is 2.5 centimeters. So then it's just going to be 0.025 meters. So 2 times pi times 0.025 squared, right? 2.5 centimeters. And then B final is going to be what? Gauss is the average field at the beginning. And let's say I do the process in 1 second. So what kind of EMF am I expecting? It's actually pretty small, right? 42 minus 6 times 2 times pi times 2 pi plus there. Right, so then you're going to have here negative 0.14, and then this is 10 to the minus 4. So if I go one more over, I can write it as, I'm just going to take the absolute value of this. So then if I go one more over, I'm going to have 0.014 millivolts. So kind of hardly noticeable. So according to that, it should be showing you 0.014. Now, what should its direction be? So if the field, this is a side view that we're seeing, north, south, right? From this end, what would you be seeing? If you look from this end, you would actually see whatever we had in our earlier example. We would see a coil like this. We would see the field coming this way, right? But first, it would be weak, right? It would be very weak. And then we would be seeing it getting stronger. As you're putting this in, it would get stronger. So what kind of current should be produced? If you're getting stronger, you should be producing a clockwise current, right? That's what the negative means, clockwise. Clockwise as viewed from this end, you see. So it always, when you say something is clockwise or counterclockwise, you always have to say with respect to who, right? From this end, it would look counterclockwise, but from this end, it's clockwise. So let's see here. Yeah, so basically the current should be this way. I wrote it wrong earlier. Like this. Yeah, because it should produce a B field to try to fight against the incoming magnet. Okay, so let's take a look now. So the value we are expecting 0.014 millivolts. See here, it doesn't tell us the scale of the voltage. I can't tell. Now let's focus on the direction for a second. What's the direction of the current flow? What direction should we say it should be? What direction? It should be this way, right? Yeah, because if you're strengthening it, it should try to fight against that like this. So it should create a magnetic field that's like that. So as I'm putting this in, this one should be going like that, you see? So let's see if that's true. No, it's going down. Hold on. Oh, you know what? They're showing electron flow. Hold on, they're not showing proton flow. Oh, okay, they're showing electron flow. So if the electrons are flowing this way, it would be like positive charge flowing the other way, right? So yeah, you're right. So let's see here. Yeah, so the electrons are going down, which means the current is going up. Yep, so it works. So you can check the Lenz's law to see if all of these combinations work. If you take it out, opposite should happen. You're weakening it, you see. Then you could reverse the polarity, put in the south pole, and then see what happens to the electron flow. Then the opposite should happen to the current flow. You see, flip the polarity. See here, if I keep the magnet there, for example, and I change the area, am I creating a current? I should be, right? It's not that noticeable. You see, change the area. Yeah, you are getting some deflection. Or we could do a case where both of them are changing. So let's say this one goes like this. I can't do two things at the same time, right? Let's say, imagine you're changing the area, and as you're changing the area, you're also doing this. You see, like that. So like a weird combination of stuff is going to happen. So when we do the math of that, we could do a couple things at the same time, you see.